Good morning, everyone. My name is Michele Gallo, and I'm the head of Aquatic Research Facilities Design here at AquaBioTech Group. Today, I will give you the first introduction to your online RAS course. In the next slides, I will give you an introduction of the production systems involved in aquaculture. I will introduce the RAS configuration. I will talk about the mass balance in RAS, water quality, water treatment, and I will give you my take-home message for today. So in this slide, you can have an overview of some of the main categories of production systems in aquaculture. I like to separate these type of production systems according to their locations between inland, near a river, or along the coastlines or offshore. Or I like to separate them based on the type of systems they are, whether they are a closed systems or an open system. Now, just to list some of these production systems, you will have going from inland to offshore, you will have ponds and flow-through systems like raceways, which are a pond system can be a closed system, but it can be also an open system, while a raceways is usually an open system. You can also have a RAS system like a hatchery, for example. Along the coast, usually you have like net pen or smaller cages, and then going offshore, you start finding larger cages or even drifting cages like in the oceans. Why are we spending so much time discussing about aquaculture and focusing on recirculating aquaculture systems? Well, the first reason is that we are a growing population and we need to produce more food for this growing population. We need to produce more protein, animal protein as well, and fish protein. And as it is now the situation of the natural resources of the oceans, it is not sustainable on a long term to keep on exploiting fisheries, produce this fish protein. So aquaculture has to increase their production and contribute more. As it stands now, you may notice while doing your weekly grocery that you have at the fish market, for example, 50-50 chances to find a wild-caught fish rather than a farmed fish. This will not be necessarily the case in the coming years, where you will have certainly a higher chance to find a farmed fish rather than a wild-caught fish. So this is how important aquaculture is for us and how more important it will be in the coming years. So what exactly is a RAS system? So RAS is the acronym of recirculating aquaculture systems. And as the name recirculating aquaculture system means that the water from the fish tanks, for example, is recirculating through a filtration systems and back into these fish tanks. So it is a closed system. In this nice and relatively simple diagram, you can see the main component of a filtration system, of a RAS system. You will have a deeper and better understanding in the next presentations from my colleagues, but I will give you an overview here. So the water leaving the fish tanks loaded in solids and metabolites is passing through a solid filtration unit, which in this case is the drum filter. Then is passing through a biological filtration step. In this case, we have a moving bed bioreactor. And from these steps on, we have a set of what we call loops. So not all the water is passing through each of these steps, but overall there is a influence of each of these filtration units. So we have a fine removal solids unit, the protein skimmer here, which is most of the time used in combination with ozone, which has a characteristic of enhancing this microflocculation, but is also disinfecting. We also have a saturation cone, which is one of the most common way to increase the saturation of oxygen, which is consumed by fish and bacteria. And then we have steps like UV sterilization, which is the steps where we try to remove all the leftover potential pathogens in the water. We have a canister filter, which is not always present, but it's useful to remove the very last fine solids in the system. And then we have the last part of our RAS system, which is, in my opinion, the real big advantage of a RAS system. I'm talking about the heat pump, or generally speaking, the temperature control. Now, the real advantage of a RAS system is actually the capacity of controlling the temperature and the environment where these fish are growing. So this is something that we always need to keep into consideration. Another important reason why RAS systems are very important in aquaculture is the amount of water consumption that they have compared to other systems. So in this table, I would like you to focus on mainly one column here, and is the first one. So the consumption of new water per kilogram of fish produced per year. Now, if you see the first number, you have 30 cubic meters of water per kilogram of fish produced per year in a flow-through system. As you can see, even in a RAS, as it's called, low level, so not necessarily with a high intensive recirculation, you have 10 times less water used per kilogram of fish. If you actually go towards an intensive RAS, you end up having 100 times less water consumed for the same amount of fish produced. This is an enormous advantage in aquaculture. When it comes to RAS system, I like to separate different categories of RAS system. The first one is what I call research RAS. In our AquaBioTech, we call it PRACTI-RAS. These are systems which are overall smaller in size, potentially with smaller tanks, but with a large number of tanks most of the times. They have a very high level of complexity and a very high level of flexibility of the system. In these slides, you can see, for example, the render 3D of a facility we built a few years ago in the Netherlands for an important feed company. Another example of a RAS system for research is the one that we delivered for an important university in Scotland, the University of Stirling. And this RAS, for example, was installed inside an existing building. Now, these kind of RAS are mainly used by researchers of public or private institutions to run trials. So they have to have a certain level of flexibility to adjust for each trials. A different category of RAS system are what I call intensive farming, commercial RAS. Now, commercial RAS, on average, they may have less tanks, but much larger tanks. In this render, you can see a prototype of a RAS that we designed for a Norwegian client. These 6 tanks are approximately 1,000 cubic meter, and the systems per se are much simpler than RAS system for research in terms of configuration, but of course, considering the upscaling, they became very complicated to run if the staff included, the staff working in these farms are not well trained. And this is why it's important that we deliver a good level of information in this online course. Another example of intensive farming RAS are RAS which are built on a barge. Now a barge is like a floating platform, and this type of RAS were and will be most probably very popular in areas where either land is not available, bare land, or where there are long distances to cover. So in this case, it is more efficient to build a RAS directly on a platform rather than building inland. In this way, you are able to move your fish farms from point A to point B. Mass balance in RAS. This is what I consider the foundation of a RAS. So the mass balance principle, it's very simple and very straightforward. Anything that we input in a closed system remains in these systems, can be transformed, but it can only leave this system through our filtration units. Now, when it comes to metabolites, for example, we can trace carbon and nitrogen and phosphorus and other components from the input, which is the main input is the feed of the fish, through the whole system, and also quantify the amount that is removed by our filtration system. This is very important because it's the only way we have to understand how to design and run a RAS system properly. And this is very important to understand also that RAS systems are mainly designed upon the amount of feed given rather than to the amount of fish. So speaking about our main input, well, the feed is the main input that we have, and feed can have a wide variety of texture, shapes, tastes, physical characteristics. Feeds are developed for different species which are feeding at the bottom, in the water column, at the surface. This feed can have a different shape according to the anatomy of the species, according to the life stage of the species. They have a different texture because they have to remain solid and firm for a certain amount of time, because not every fish is feeding immediately, for example. They also have a different content of nutrients according to the life stage, according to the type of fish, whether it's a freshwater or a seawater species. So this is very important to take into consideration. Consumption. Well, our fish are mainly producing a set of metabolites such as CO2 as a result of respiration, solid fishes, and as part of the what we call urinary losses, we have nitrogen as a main element. And this nitrogen is excreted by the fish as total ammonia nitrogen, which is a combination of ammonium and ammonia. Now, overall, we can say that fish are eating, the more we feed the fish, the more these fish are able to eat, up to a certain point. But this is more or less the trend that these fish have over a long term. However, and this is very important to understand the complexity of aquaculture, fish are not growing like plants indefinitely, but they have actually a particular growth curve. As you can see from this graph on the right, which is coming from an old illustration of a researcher called Fomberta Lamfi, we can see the growth of a fish, let's say an average fish, and we can see that this fish is growing much faster at young age, and slowly the growth rate is decreasing up to a certain point where the growth is almost null. What does it mean? It means that when we are planning our production plan for our farm, for example, we should consider at which point we want to harvest our species. Do we really want to harvest our species close to the highest weight, where maybe we need to feed a lot but it's not growing of the same amount, or do we want to harvest our fish, let's say, in between? This is an aspect that every fish farmer is considering, and this curve is slightly different depending on the species, but the shape remains more or less the same. And this is why, or is one of the main reasons why farmed fish are on average smaller in size than wild caught fish, simply because they never reach the full maturity in a way. Removal. So we said that the RAS is a recirculating system, a closed system where our filtration units are removing a metabolite. In this slide, for example, you can see how a biofilter removes or converts nitrogen. So a biofilter is one of our filtration units. It's a container full of water where floating plastic biomedia are covered of bacteria, and these bacteria are autotrophic bacteria mainly, but also heterotrophic and other small organisms. The way these bacteria work in general is that the more substrate they have, in this case nitrogen, the more they are able to remove, again up to a certain point where another element can become the limiting factor for their consumption. In this case is oxygen. So the removal rate, for example, of the biofilter is a function of the concentration of the substrate, in this case total ammonium nitrogen, and the level of oxygen in the biofilter, which define the point at which our biofilter will not remove anymore if this concentration increase. Another way to remove is, for example, by dilution. Now, dilution is a very simple concept. What we do is we exchange the water. We remove dirty water and we add clean water to the system. The level of dilution of a RAS system is giving us the idea of how intensive is the system and how concentrated is the water of our system. And this is a choice also of a fish farmer, for example. But it's also a function of the level of metabolites which we have in our water. Now, I will go through another part of this presentation, briefly mentioning some of the important parameters of the water quality. However, you will have a better and longer explanation in one of the other presentations from my colleagues. Every fish is different, and every fish has slightly different requirements for when it comes to water quality. Some of them, they may be similar, but they are not always the same. So we always have to understand the biology of our species and understand what are the requirements of our species. In this table, we can see, for example, some of the main water quality parameters for only 4 of the most, let's say, popular species for freshwater: African catfish, European eel, tilapia, and trout. As you can see, some of them are what we call warm water species, some others are more cold water, and this water temperature has also an impact on the amount of oxygen that these fish require. And these species are also tolerant to different level of solids, CO2, nitrogen, and etc. So these are all aspects that we need to consider when it comes to farming different species. I mentioned water temperature. Now, water temperature is impacting a lot of aspects. So it's influencing the metabolism of fish, but also bacteria. Is impacting the body composition of our fish. It can harm the immune system of the fish. It has a strong relationship with the sexual maturation of certain species, which are triggered by different seasons. So we may experience at a higher temperature certain species start maturating sexually, and this is not actually a good aspect of fish farming if it is not under control. Temperature is also affecting the bacteria activity in a similar way as they do with fish metabolism, for example. Salinity. Now, salinity is a very important parameter, but is also quite straightforward. We know that there are species that are tolerant to fresh water, species that are tolerant to seawater, but we also have species which are tolerant to a range of salinities. And we have species like Atlantic salmon, where they are tolerant to fresh water at the beginning of their life, and they become tolerant to seawater after a certain change in their body physiology and body composition. Now, the salinity is impacting a lot of the physiological processes of a fish, but is also impacting the water quality indirectly somehow. For example, is reducing the nitrite toxicity. pH and alkalinity. Now, pH and alkalinity, together with the CO2, carbonate and bicarbonate, are part of the carbonate equilibrium. My colleagues will discuss more about this aspect, but it's important to consider these two parameters, pH and alkalinity, always together. Carbon dioxide, which was part of my early studies and is one of my main focus here at AquaBioTech, is one of the, let's say, new water quality parameter when it comes to interest of the field. It is not well understood in terms of effect on fish physiology and also on effect of water quality. We know that different level of CO2 can cause different problem to fish, but we also experience that these levels are not always affecting the fish in the same way. So there must be a relationship with other water quality parameters, which we do not fully understand. What we know is that carbon dioxide in the water is decreasing the pH of the water, is increasing the acidity of the water, but is also on a long-term exposure can seriously harm your fish, at least by decreasing the growth rate, if not causing mortality. And this is why we always take care of the removal of these metabolites in the water. Oxygen is probably the main limiting factor for fish. It's impacting the fish growth, the feed intake. We can stretch that the higher is the oxygen, the higher is the feed intake of the fish. It's impacting the bacteria metabolism, as it is somehow helping certain bacteria to outcompete other bacteria. It is also temperature dependent, which is one of our main concerns, as we need to consider that injecting oxygen in a warm water is not as easy as in a cold water. Even though limited oxygen is or can be lethal to fish, we need to consider that an excess of oxygen, so a gas supersaturation, can also be very harmful for juvenile fish or for larvae of certain species. It can immediately cause a gas bubble trauma, which is lethal. Total ammonia nitrogen, nitrite, and nitrate are the three forms of nitrogen in the water. So fish excrete what we call total ammonia nitrogen, which is a combination of NH3 and NH4, and bacteria in our biofilter are converting through nitrifications this total ammonia nitrogen first in nitrate and then in nitrate. Sorry, first in nitrite and then in nitrate. Now the nitrate is our end product of nitrification, which will accumulate in the water unless we dilute the system by having a water exchange, or by including in our system a denitrification reactor, which is a different type of biofilter with different type of bacteria, which are metabolizing the nitrate into nitrogen gas, which is volatile and therefore can be removed from our system. Now, nitrogen in the form of NH4 and NH3 are very pH dependent. As you can see in the graph on the right, if we increase the pH of the water, we increase the percentage of this total ammonia nitrogen, that is NH3, compared to NH4. Now, it's important to consider that NH3 is much more toxic than NH4 for fish. So this is how can be lethal not having control on the pH of our water. TSS is a general category. We call it total suspended solids, and in general defines the amount of solids in the water. Now these solids are coming from mainly uneaten feed, fish excrement. They are impacted by the water velocity, so they can sediment or remain in suspensions. They can clog fish gills. They can create a substrate for bacteria, pathogens, or they can even trap nutrients. They also increase the water turbidity. They can clog pipes, and they certainly decrease the biofilter performance. So, together with all these parameters that I mentioned, I want you to consider that there are a long list of other water quality parameters, which are not always measured. They are not removed by any filtration units, but they are there. Some of them are like humic substances that gives a color, like a brownish coloration to the water. We may have heavy metals, which can be contained either in the feed or they can be already in the water. We may have hydrogen sulfide in some part of the system, which we want to avoid as much as possible. We have off-flavor compounds, which are, for example, produced by certain algae. And we have hormones and pheromones, which are the way fish communicate in the water. Why we have to consider all these substances and parameters? Because in the end, the water of a RAS system is quite similar to a fish soup. Even though you know all the ingredients, the final taste is a combination and the interaction of all of them. And this is why when it comes to water quality of a RAS system, I always like to have a holistic approach and understand all the interaction between each parameter. This is very important because if we try to handle one parameter at the time, we might lose the track of all the other parameters. So this is why we should always consider the complexity of the system we are handling. Now, in the last part of my presentation, which is going to be quite brief, I will quickly go through the main filtration units of a RAS system. But I want to start by giving you, let's say, an introduction over this type of technology. Now, aquaculture, in a way, took some of the technology of wastewater treatment and managed to reduce the size, in a way made them more efficient and made them working together in a slightly different way. But in terms of level of technology, it is still a working in progress in a way. Other sectors, they have a higher level of technology, and aquaculture is slowly keeping up. So there are new technologies that will be included in the next generation RAS systems, but they are not well understood yet. Now, the first one is the fish tank. The fish tank can have different shapes, different size, different materials. Mainly, or at least very popular, is like circular tanks. Now, what are the factors that we are considering when it comes to a fish tank? Well, we want to know what is the tank turnover of our tank, which means how fast the water leaves and comes back. We use these parameters, the tank turnover, to understand what is the flow of our system. Now, this tank turnover is also affecting the water velocity in the tank, and therefore fish distribution in the tank, solid distribution, and solid removal in the tanks. Our solids removal unit, it's most of the time a mechanical unit. It can be a drum filter, it can be a belt filter, it can be a cartridge filter, and you will see more examples from my colleagues. What they have in common is that they simply are sized for the type of solids that you have, which are defined by the life stage of the fish, by the number of fish, and by the type of fish. So if we have, for example, small fish in the tanks, most probably the mesh size of our drum filter would be smaller than if we have large adult fish. The biofiltration is carried out in our biofilter, and we have different type of biofilter. Now, here at AquaBioTech, we use most of the time, if not always, a type of biofilter called moving bed bioreactor or moving bed biofilter. Now, this biofilter is considered one of the most efficient in terms of footprint, in terms of energy efficiency, and in terms of removal rate. And it's probably the one that has the least number of problems on a long term. Now, in this type of biofilter, as I mentioned before, this plastic biomedia that you can see in this picture is covered by these bacteria, this kind of fluffy bacteria, which are uptaking nutrients in the water and increasing their biomass. And by converting the metabolites in the water, they are improving our water quality. Now, this is our probably most important unit in our filtration system, and is also the one that is a combination of a mechanical and a biological type of unit, which requires a lot of understanding, a lot of knowledge, and a lot of also testing in a way to understand how we can set every aspect of this biofilter at the best possible way to remove the to convert the largest amount of metabolites. So my take-home message here for this presentation is try to design your RAS around your fish species, most if possible. But be flexible and keep it simple, because these RAS systems are used by humans, are used in different countries, by people who are not always highly educated or highly specialized. So they have to be simple to use. We are what we eat when it comes to fish, so we always need to consider what type of feed we give to our fish, because it will have a result on the type of taste that these fish have. Always consider the mass balance of your system, because this is the only way you have to make sure that your system is sized correctly. It's the only way you have to understand what happened to the metabolites produced by your fish, and it's the only way you have to predict what will happen to your fish if something goes wrong. Feed your fish, which seems quite straightforward, but also feed your bacteria, because without your bacteria, your biofilter will not convert and remove metabolites, and your fish may end up dying. And keep the water clean, not only from an aesthetic point of view, but also because it's important to keep control over the fish biomass. It's the only way we have to check if there is any abnormal behavior, if there's any mortality, or if there is, it's the only way we have to anticipate any problem. If you have any further question, curiosity, or you would like to discuss more about RAS systems, feel free to drop me an email. I'm sure that my colleagues in the next presentations will go in much more details in every aspect of RAS systems, from water quality to RAS units, to operation and maintenance, and I'm sure that you will have a much better understanding of RAS system at the end of this course. Enjoy and have a good day.